Yes, now I'm back. Okay. So, a little bit more chemistry before lunch. So, interestingly, remember how this came here? I wanted to ask, but this was this reaction, right? And I had prepared the question, why is that thermodynamically unfavorable, contra to thermodynamic? I just want to make you aware of something, right? This clearly cannot be an answer. You essentially phrase the question in a different way, because thermodynamically unfavorable, contra thermodynamic means nothing else but being thermodynamically unfavorable, right? And so you're answering, this answer like this, you're actually repeating more or less the contents of the question. So always be aware of this, that you need to be precise, and I'm not sure how things usually work for you here. We are supposed to give a small exam here at the end of the course, and it will, Professor Zakar told me, it will be multiple choice. I have to think very hard about multiple choice questions, but you have seen I already have a few, so don't worry, it will not be very hard. But very often you have to write written answers or write schemes and things like this, and I see this very often, that the answers are imprecise in the way that they don't explain what it is, that they essentially in a different way say what was asked, but without giving an explanation, right? And so here in this, we talked about this, right? If you ask about thermodynamic, favorable or unfavorable, typically what I like always to do is I simply analyze the bonds which change. So I have a carbon with a CO double bond here, and now in the end here in the product, I have a CC double bond here, and so I know the CO double bond is at least 20 kcal per mole more stable, and so that type of analysis. Okay, here's another reaction which is contra-thermodynamic, and these are the Paterno-Büchi reactions. Paterno-Büchi reactions make use out of it that you, again, excite a carbonyl group around 350, 360 nanometers, and then they can also undergo 2+2 cycloadditions. And they can do this even with aromatic systems like furane. And here you see the example for this, where you have done a 2+2 cycloaddition. And again, clearly, this is contra-thermodynamic, and I will actually show this to you in a little bit more detail in just a moment, because we have calculated this. This is about 24 kcal uphill in this reaction. And why is this? Because we are breaking the aromatic ring, aromaticity in the furane about 15 kcal. We're making a strained four-membered ring, so we're introducing ring strain. That's another 27 probably. So it's 27 plus 15 is 42. But then, of course, we're exchanging the pi bond for sigma bonds in the carbon-carbon regime. That should be up 10 kcal, but also we are converting the CO double bond to the CO single bond. So that again brings it downhill. So there are a couple of factors, and in our calculations we calculated that it's about 24 kcal uphill in this reaction. And then so here you have another one. You see, and here again it's another 2+2 cycloaddition. Again, I've written contra-thermodynamic probably for the same reasons. You still make a four-membered ring here, you dissolve the carbon-oxygen double bond. The one thing to realize here is that this is a reaction where you build a more strained ring system, but you also have strain release here, because in norbarmene, if you ever build this, you can already see how strained this is when you have a model and put this together. So these are the typical strained alkenes, and therefore these type of reactions work very well. It goes with very, very good yields. So here's my other question, which is very important to consider when you look at energy transfer processes. If these reactions are contra-thermodynamic, so starting material and then my product is higher in energy, why do they not go back? Why do they go to the product, but why don't they go the way back to the starting materials? Again, under the reaction conditions which we do, we shine light on there. Why do we stop at the Why does the back reaction is not taking place? Are you okay with this concept? That probably more or less applies to any type of these photo 2+2 cycle additions. No idea? Well, this is really important from the conceptual point of view, right? No idea. Okay. That's a fair answer. I think it's very good to admit this and say, I don't know why. In an exam, I would now probably ask, okay, so tell me how the forward reaction works. Right? And if you go back to this and say, look at the forward reaction, how does the forward reaction work? My carbonyl group is absorbing light at around 365 nanometers. I excite it, and it does the 2+2 cycle addition. If I want to excite the product, what would I excite? The carbonyl group is gone. That's probably the best chromophore. Alkenes, we had that one table, around 250 or so. So this is the key idea here. In the products, very often, they don't absorb light any longer, or they absorb light in a much shorter UV range one. So I have in my starting material, I have something which will absorb at 365 nanometers. That's the carbonyl chromophore here. In the product, I might have at best the pi system of my enol, and this will, and then if you measure a UV, for example, you will find out that this is not absorbing at 365 any longer. If anything, it absorbs at a much lower wavelength. So keep this in mind. This is the idea why all these reactions can work. If they are thermodynamically uphill, they will not react back because the reaction pathway, the light-induced pathway, is not there any longer. If you heat this up, or if you do, I showed an example in a moment, if you do like a Lewis acid catalysis activation, you might open up the ring and reform the furane. Absolutely. So this might happen, but not under the photochemical reaction conditions. Okay, good. So here's the reaction from our lab. The Paterno-Büchi reaction is furane, as I showed you on the previous slide, was known. But we liked this. We wanted to look at this, and probably you see the idea. We did cyclopropanations on furanes, and then I told my co-workers we did this for a long time. Now let's do some other ring systems. And so then they came up and say, okay, we do the Paterno-Büchi reaction. And I said, well, this is already known. And they said, yeah, but we can do something more with this. Let's just have a quick look at this Paterno-Büchi reaction. The phenyl group is on the same side like the hydrogens. Why is this? Should have put a question to this, but I didn't do this. Forgot to do this. Why is from the stereochemistry point of view, why is the phenyl group at the same side like on the same side like these hydrogens here? Anyone want to give me the keyword which you might want to mention? It's again a question of, I draw it over here because I can draw this here relatively nicely. It's again a question of a convex and a concave phase of a molecule, right? We have again two rings, two small rings, 5 or smaller, and they will have a concave phase and then they have a convex phase. And the substituents, okay, I need to put in the oxygen here, and then the substituents will orient themselves on the convex phase. And so this is essentially, this means it's the same side like the hydrogens, right? So this is again on the convex phase. So keep that principle in mind, because that is seen, because we do so much chemistry in general on ring systems. That's a very, very important concept, and makes reactions very, very selective. This is the only diastereomer which you are observing. You're not observing the other one where the aryl group would have gone into the concave phase. Right? And so in this case, what they did then is show the mechanism on the next slide, but we are able to convert this into a cyclopropane. Right? And again, if you look at this, my gut feeling was that even this should go further uphill, because we're now making from the strained ring here, we're making maybe an even more strained ring here. But then when we did DFT calculations, we found out that we're actually going a little bit downhill. And the reason for that is probably, again, that we're making CO double bonds here. Again, that's a thermodynamic typical driving force. But what we like about this reaction, as I'll show you how this works in a moment, is you start with two compounds, and these are renewable resources. The furan, we talked a lot about this, such benzaldehydes come from lignin probably as well. And so we do a 2+2 photo reaction. It's 100% atom economic. It's a light reaction. It's absolutely clean. These reactions are close to quantitative. We store 24 kcal per mole into the product. And then in the second reaction, we are actually doing follow-up chemistry with these oxytans. And this was indeed not known to make these type of cyclopropanes. Let me show you how that works. Right, so the way we can activate these types of oxytanes is that we are using a Lewis acid, and you can see we can use very little of the Lewis acid. The Lewis acid is coordinating, and now it can open up the bond, and it can do it in two ways, right? If it can open up the red bond, and it can could open up the black bond. If it opens up the black bond, the system goes back to the starting materials. And that's why we think that such a chemistry might also be interesting as energy storage systems. But if it opens up the red bond here, then we would form this cation. And you see how we have chosen this. We have chosen a substituent here, which is a donor, a good donor. So we need to choose this substituent in order to open up this bond selectively. Our R group should be able to stabilize the positive charge here. And then this chemistry works very well. And then we have an enol and a cation here. And then if this enol is attacking this positive charge here, so you form the new bond between this carbon and this carbon. You form the three-membered ring, and then in the end, if you hydrolyze the acetal, so another water addition onto this side, and then hydrolysis of the red bond, you form two aldehyde compounds. And so we like this chemistry because at least it's one example where we do not need any pre-activation. Again, we talked about cyclopropanes. Usually the carbines, we are either making from diazo compounds, or we're making them by making carbines, for example, dichlorocarbines from chloroform. So typically all strong bases, stoichiometric bases, and here we have a entirely we have a complete light type reactions in order to do this. So let's look at a few more examples. This type of reaction is very often used in natural product synthesis, and again to make highly congested ring systems. Here's an example from my colleague Thorsten Bach from the TU Munich, and he showed that you can do this type of 2+2 cycloaddition. You see, you get a 2+2 cycloaddition between these two systems, and you can do you can get such a ring system out of this. That was 2003, and probably if you would try this today again, you would maybe use a photocatalyst, which would allow you to absorb more in the visible light range. You see, they had to irradiate here with hard UV, and that was because you don't have anything really which absorbs light well. The alpha beta unsaturated carbonyl compound, that is probably your chromophore, which you excite, and but you need pretty short light wavelengths. So let's quickly talk about how is this energy transfer, how is the principle for doing this. And there are two types of ways this could go. There's a Förster energy mechanism, and this simply you bring your photocatalyst or your donor, you bring it into the excited state, and then it transfers the energy to the acceptor. Let me show this to you again. Transfers the energy to the acceptor, and it goes back to the ground state and is lifting up your acceptor, your substrate, for example, to the excited state. The second way you have is the so-called Dexter energy transfer. That probably always is happening in photocatalysis. And this is, again, you have your photocatalyst, your donor, you have it in the excited state, but now if it is doing a collision with the acceptor, what simply happens is that they exchange the spins. So from the acceptor, one electron is exchanged to the ground, to the lowest orbital of the donor, and the excited electron from the S1 molecule from the donor becomes the S1 molecule from the acceptor. And in order to do this, you need to be able to have the compounds have to be close to each other. So like this is shown here in this review. This is a review on energy transfer from Professor Frank Lorios, which I can highly recommend, which is really explains things and gives many, many examples in a great way. And so you see the really important thing is that these two molecules can come close so that they can exchange the spins which you need in order to exchange from your excited donor coming to an excited acceptor and do this. And so typically the model which is being used is you have the isolated molecules, they come close to each other, they have a collision complex, exchange the spins, and then they might diffuse it again, and you have done the energy transfer in this scenario. And so then if you want to do this, it's very important in order to exchange these spins, it's very important that your triplet gap matches. And if it doesn't match, it cannot do this, right? So so here, this gap here needs to be similar. Let me see, do I have it? No. So this gap and this gap needs to be very close to each other in order to have that efficient energy transfer. And so you need to know about this. And the good thing about this is that, again, you find it in the literature. You find for almost any type of photocatalyst, you find tabulated the triplet energy, and so therefore you have the gap to the ground state, and you see it's different for each catalyst, and probably not surprisingly, it correlates very well with the absorption. So of course, if you need higher energy light, then you can reach an excited state which is higher in energy. And you see here the ruthenium bipi has a triplet energy of 46 kcal, but then if you go to iridium, so this here absorbs around 400. The iridium bipi, ruthenium bipi is probably 450. The iridium PPY is around 400, and then the benzophenone is 350. And you see the triplet gap is becoming bigger and bigger this way. And so therefore, you need to know about this need to know this about in order to choose if you have a substrate, in order to be able to efficiently match the triplet energy of your substrate. And again, a lot of that is already known in the literature with a triplet gap of your catalyst. But that also tells you that it makes a lot of sense sometimes to try, if you don't know the triplet gap of your substrate, it makes a lot of sense to try different photocatalysts to get an idea. And then maybe in some cases you use a photocatalyst which does not have the right triplet energy, and then this might be the reason it doesn't work. But in principle, the reaction would be okay. And so again, there is in this review from Frank Lorius, very nicely, he lists a lot of these triplet energies from a lot of the photocatalysts, and then he also shows substrate classes, so quite a bit of them. And you can simply check, and then you can simply see, okay, I have a triplet energy in this substrate of 70 kcal, and so therefore I need to go to a catalyst which is close by or ideally identical in order to do this. So again, this makes the type of chemistry very, very predictive. And then you can sensitize different types of molecules, and one molecule which is very important, and that also very often comes to the question, should I run the reaction under oxygen or not? Oxygen itself can get sensitized, and there are many dyes which can do this. Methylene blue might be one, rose bengal, but also ruthenium bipi. Ruthenium bipi can sensitize oxygen, and what you are then getting, you bring the oxygen from the triplet state to the singlet state. And the singlet oxygen, that is a dienophile. This can do 4+2 cycloadditions. And so with dienes, it's a very common reaction, a very efficient reaction, that if you do a photoirradiation with oxygen, that you get the Diels-Alder adducts. So it's not a photochemical 4+2 cycloaddition. It's just that you bring your dienophile, which is in the ground state, is in its triplet state, you bring it into the form that it can do a concerted reaction in this, and that is the singlet state of oxygen. And so that is what the light is doing, but the cycloaddition itself is not a photoreaction, it's a normal thermal 4+2 cycloaddition. And you see that this works very, very well in this case here. So that's again not that old of a publication. And these type of NO peroxides are a type of compounds which people are very interested in, because artemisinin, it's the number one anti-malaria drug, and this has exactly such an NO peroxide structure. And I guess malaria here, you can also, I'm always nervous when I see mosquitoes or here, but I think malaria in the cities is pretty well in check. But malaria in India, because you have such hot weather, is still something which you have here in this country, right? And fortunately in Germany or so, it's not something we have to battle. Okay, so, and then we have shown the photochemistry on these type of systems by electron transfer, right? So the Yoon group, and again, there's a publication from Yoon, they showed that with an electron transfer catalyst, you can make the radical anions, especially if you have acceptor substituents here, make the radical anion and then do the 2+2 cycloaddition stepwise. But the Yoon group also showed that you can do this by energy transfer, and you see that the advantage this has is if you go through the energy transfer mechanism rather than through the electron transfer, you can do this with different types of substrates. Because with the electron transfer, you needed an acceptor here, because otherwise the electron would not be able to get efficiently transferred. It would not be a good electron acceptor. Now here with the aryl groups, it is very easily excited essentially to the diradical, right? And you have the aryl group which stabilizes, here it is written, stabilizes essentially the radical species here. And so now by energy transfer, you will be simply able to do the 2+2 cycloaddition, This is, of course, what we have seen in the previous examples as well, like here in this example, here as well. But what the U group was showing, and that's why I said here in this reaction, you have to irradiate with very high energy light. But what the U group shows here is that because you're using a sensitizer, which absorbs in the visible light range, that you can go through longer wavelengths light and do the 2+2 cycle addition sensitized, so you're not directly activating this to the diradical, but you go to the excited state of the iridium catalyst, and this will then do the energy transfer to get you the activated substrate here. And so we talked briefly about the idea to use these fluorescent light bulbs, right? I think it would have been nicer if they would have used an LED here, which would absorb, where they irradiate exactly at the wavelengths of the catalyst. With these CFL lamps, you always have UV parts on there. And so it's a little bit harder to deduce what you are actually, since you have such a broad range of wavelengths there, it's a little bit harder to, analyze what is actually the activation of that molecule. And you see here they did some very impressive chemistry on this. So they did these 2+2 cycle additions, and that works, makes these highly congested systems. Here you can see this yourself. If you're forming the one ring here, and then you form the next forming ring here. And again, photochemistry allows you to do this, right? Because the energy you need, you bring in through the light. And then on the other hand, this compound has no chromophore to take the energy, so this is why the reaction also in the sensitized way is not going back. Okay. Here's an example which I would like to show, and I hope we have the time, something I have also prepared for the tutorial yesterday, and as I said, we're a little bit behind of what I thought we can do. This is now an enantioselective 2+2 cycle addition, and that again comes from Thorsten Bach, who's doing a lot of asymmetric photoreaction. And here's a very exciting system. So you see he has a photocatalyst, and so this is here the photocatalyst, which is typically doing the energy transfer. But then the photocatalyst is attached to this chiral unit here. And this chiral unit is an amide, and so it can recognize other amides. You see, by complementary forming hydrogen bonds, it can recognize the substrate. And so he was using this substrate with this catalyst, and you see this substrate has an amide, and it can get recognized and coordinated here. And so then he's ideally pre-organizing the photocatalyst with the substrate. And so the energy transfer comes from the photocatalyst to the aromatic system here in order to excite this. But the important thing is it gets only excited when it binds to the catalyst, because only then it is close enough to do the energy transfer. And so then when you have the energy transfer, then you are able, from the excited state, to do the 2+2 cycle addition. And if you look at this, if you look at this system here, you can probably easily understand that this double bond would come from below and not from the top, because on the top your photocatalyst is in the way. And so the Bach group could show that you can do enantioselective, and you see fantastic enantioselectivity to highly strained ring systems to make such kinds of compounds. And the other thing which is quite important in these type of reactions is, we already said that it is very important that you match the triplet energy of your catalyst, and that the triplet energy needs to be at least as much as your energy gap. And one thing to realize is that you might be able to change the triplet gap of your substrate. And the way you might be able to change it is that you by Lewis acid coordination, you can lower this. The same thing like Lewis acid is lowering the LUMO, you have the same thing, right? You have the HOMO-LUMO, that this is your gap. If you bring in a Lewis acid, you might lower the LUMO. And so the triplet energy can change. And again, the Yoon group here showed and measured this, that this is happening. So this substrate had a triplet gap of 54 kcal per mole, but if they coordinate this with scandium, with a Lewis acid rare earth metal catalyst, then the triplet energy drops to 33. So quite a lot, 20 kcal. And this allows you now to do the sensitized reaction with a ruthenium, in this case with a ruthenium photocatalyst. And he is using this for 2+2 cycloaddition with this diene, and you see you're forming one new cyclobutene here between this double bond here and this double bond. So this gets excited, this makes this double bond reactive, and then 2+2 cycloaddition with the ground state of this diene is happening. And so the one thing which is important to understand is that through the coordination of the Lewis acid, you might make your system more reactive. And because you make the triplet gap smaller. But the other important realization is that in this scenario, because you're choosing a photocatalyst where the triplet energy is not sufficient to overbridge these 54 kcal per mole, what is important to understand is that this molecule alone, without being coordinated to the Lewis acid, will not react. Right? It could be, in principle, if the triplet energy would be higher than these 54, then we could also have a reaction that this cyclization between these two molecules would occur in the absence of a scandium catalyst. But the way very cleverly chosen is that your triplet energy of the catalyst is only sufficient when the Lewis acid is coordinating to this. And that way, and that's what the Yoon group did, they have one of these chiral bisoxazolene ligands. And with the bisoxazolene ligand, so these is, I think we have seen some of these ligands before. All right, so these bisoxazolene, here's a pibox ligand, so this has a pyridine in between. So these are these type of chiral ligands. And he is using a T-butyl group here, so it is this type of ligand structure which he has. And so then with the scandium scandium triflate, you are going through you're forming such a complex. And so again, please understand that this is not the photocatalyst here, right? Your photocatalyst is the ruthenium catalyst, but you do the photocatalysis in the presence of a chiral Lewis acid, and the reaction only works when the Lewis acid coordinates to the substrates, because only then you can overcome the triplet gap of the substrate, which in terms what the catalyst is offering. And you can see this is, again, I think, a very spectacular result, that he gets good yields, but fantastic enantioselectivity. Okay, I must have duplicated the slide twice. Okay, here's another thing which I really like in this concept of uphill catalysis. It's a different type of idea, and in order to introduce this chemistry I want to show you, I would like to ask you, what is the smallest cycloalkene which can tolerate a trans double bond? Right? We all know normally cyclic alkenes like cyclopentene, cyclohexene, the double bond is cis. If you want to have the double bond is trans, how big must the ring be at a minimum that that compound is stable? And I have a spelling mistake there. It should be cycloheptene, not heptene. Okay. So you guys, very good, try to decide if it should be an 8-membered or a 9-membered ring, and definitely it's not a 6-membered ring. That would be much too strained. So indeed, it's the trans-cyclooctene, which most of the majority of you guys have suggested here. And so with this said, there is something pretty exciting you can do. And also I talked to one of the, not sure if I see him here in a moment, about one of your projects where you would be trying to isomerize a trans double bond to a cis double bond in order to get a cyclization. The reaction I would like to introduce to you here, this is from Jimmy Weaver, and I think in this context he used this term uphill catalysis, where he's doing the opposite. He is taking a small ring, you can see here, this is a 7-membered ring, so that would normally not be stable, a trans-alkene you cannot form in this. But what he's doing is he's irradiating it. And so in this way, it starts, if you are irradiating alkenes, you will get a equilibrium of the cis and the trans alkene, right? And the reason this probably works is you go through the excited state, you can again draw this like as a biradical, and in this excited state you have dissolved the double bond, so you can rotate around the single bond, and so you can get cis-trans isomers, and you see what I asked. And so the exciting thing about this is that if you would have what he is doing here, if you would have a if you would have such a cycloheptene here, that is usually would not be very reactive for, and certainly not for a thermal process, right? If you have a 2+2 cycloaddition, we all know that this will only work photochemically, but it will not work thermally. But what he's doing here is he is irradiating this with an energy transfer catalyst. So clearly this has not the can irradiate this in the visible light. And then what he's doing is he's isomerizing in an equilibrium the cis alkene to the trans alkene. And in the trans alkene, he's inducing, of course, incredibly strain. In the cycloheptene, it is calculated that this should have 36 kcal strain energy, so that's much higher than a cyclopropane would have it. And because of this now, it suddenly is doing a 2+2 dimerization with one of the cis alkenes. And the reason he could find out that this is not a 2+2 cycloaddition is because the stereochemistry here is in a way that it has to come, that one of them has to come through the trans alkene here. And of course, it's not a concerted reaction any longer, it's probably stepwise, because the 2+2 thermal reaction is not allowed by the Woodward-Hoffmann rules. But here it goes probably through a diradical type mechanism, goes stepwise, and the reactions are very efficient and can occur. And he showed later on that this type of chemistry can not only done for 2+2 dimerizations, but you can have, for example, a diene present and then get Diels-Alder reaction going, which would under thermal conditions not work because the homo-lumo difference would be too big. But by introducing strain into the molecule photochemically, then the reactions suddenly start to work because the strain release is really the driving force. And here's another example what the photochemistry can do. And again, I think this is very exciting. This is work from the group of Frank Glorius, who showed that the energy transfer conditions actually allow you to de-aromatize arenes, and the one which he's using are these isoquinolines. Isoquinolines are not quite as aromatic as benzene would be, or as naphthalene would be. And he could show that under the energy transfer conditions with the right iridium photocatalyst, you go through such a diradical, and then this diradical can actually do, again, it's a formal 4+2 cycloaddition, which occurs now, but it's not a concerted one, right? It's essentially a radical type mechanism where he is then combining the diradical with the alkene. And so this way he's able to do dearomatizations of very simple flat molecules. This type of chemistry is often coined escape from flatland, right? You have flat aromatic systems, and now you make 3D scaffolds. And that is indeed, again, very nicely and very easily done, and could not be really done by any type of other methodology. And I can also show you that typically in the dearomatization, or typically in these uphill type catalysis, there are also single electron transfer processes, of course possible. And that is an example here from our group where we photocatalysis, but this time again by Photoredox catalysis, we are making the radical here, which I have shown you previously already a lot, by the oxidation of the malonate. And the way we have designed the system is that if this reacts with an alkyne, show you the mechanism on the next slide. If this radical reacts with an alkyne, we are having these vinyl radicals, and the vinyl radicals indeed are able to do a dearomatization here, and because the vinyl radicals are very unstable and very reactive, they go into the arene and will ultimately do the dearomatization of this type of system, right? And so the photocatalyst in this case helps us to make these highly reactive radicals, which then get relayed further with the reaction of an alkyne, and then ultimately the dearomatization. The one thing which I think is always careful, where you have to be careful, is, again, we thought that this is maybe something which is thermodynamically uphill, and if you consider usually, how do I convert a benzene? How do I convert this to a cyclohexadiene? You see, this is ultimately what we are doing. How do we do this normally? What is the reaction? Which one? Say again. It's a Birch reduction, right? So the Birch reduction uses lithium and ammonia. So again, high energy reagents in order to do the reduction. And here, of course, in a different setting, because we're making a spiral cycle, but we're making the same type of cyclohexadiene as a product. The one thing to be careful about this is always, like, how uphill or downhill is this? And at least for our reaction, we calculated here that it's probably not, it's relatively thermoneutral, because don't overestimate the aromatization stability. We cracked the aromatic ring system here. So we're going, we overcoming the aromatic stabilization, that is 35 kcal. But then at the same time, we're making sigma bonds at the expense of a triple bond, right? And so when we calculated this, it was more or less thermodynamically the same way, the same thing, but from the transition state, from the activation here, the dearomatization, of course, had a very high barrier, and that is something which we were able to overcome by generating photochemically a radical and then going through a radical pathway which has a lower barrier than the closed shell pathway would have had to go to the products. Okay, so this is what I wanted to briefly tell you about energy transfer. Now I need to think about, because we started, Sangeeta, help me, we are doing until when? Until 1:15, right? Okay, so there are essentially, there are two things I can do. I think I still have a few questions from this tutorial but I think maybe very quickly. I wanted to go over one thing which I felt is important. Wanted to go with you, and before we start on something new. Because I think in all these scenarios it is important to always think about, when we think about any type of photoredox catalysis, how do we close the cycle? And this might be very different even for the same reactions. And for this, I wanted to give you an example. We talked about this already, and I think we have drawn this, and so I'm not going to ask this again. Oh, you already answered this. It was interesting because I had it in the other presentation, and then it is doing the same thing. So here's another reaction which we did in our group, and let me see. Yeah, and so this is a reaction which takes a carboxylic acid and then it decarboxylates the carboxylic acid, and then we are in the same scenario which we had before. I told you that when you do this with copper, so you see you go from copper 2 and then it's doing a dissociation, a homolysis, goes to copper 1. It makes the carboxyl radical. The carboxyl radical loses carbon dioxide. And so as the first intermediate, you get this radical, and this radical traps oxygen very efficiently. So you get this, and then, so since you have copper 1 here now, your copper 1 will coordinate with this peroxyl radical, and you see in this way it becomes copper 2 again. And if this is now, so let me just, so that it becomes clear, let me just put an X here so that we can easier see what the oxidation state is. And if this is now eliminating the hydroxide here, you are forming the carbonyl group, which is the carbonyl compound, which is now has lost one CO2, and you're regenerating copper 2, right? Because it has eliminated copper 2 hydroxide. So that's why I think it's okay, right? The catalytic cycle is closed, everything is fine. There was a very interesting paper from the Yoon group again, 2 years ago, 3 years ago, came out in Nature Chemistry, and see what they did. They are taking also copper 2. They also do a decarboxylation, but they do this in the presence of a nucleophile. So the sulfonamide is the nucleophile here, and then they get, you see, they get the truncated. I gave you an R group too many here. I was a little bit too fast here, so this should be gone. So they get the truncated one, which they couple here with the nucleophile. And you can see what they do is they do the whole chemistry in a glove box under nitrogen atmosphere, because they need to be absolutely sure if you have oxygen presence, once you form the decarboxylated radical, if you have oxygen present, it really traps it immediately. So they needed to do this in a glove box, and then this way they could get the coupling between the radical they are forming and the nucleophile. So here's my question. How is the catalytic cycle closed? If you think about this, if you go through this reaction, how do you close the catalytic cycle? Or how does How does this work? Just go out because I think I will want to have a new page here in just a moment. Yes. Because we need to think about the mechanism. And for this we need a new page. So do we have any answers? I show you the reaction again. You see, you start with this. Let's already start on the reaction mechanism. So they start with copper 2. They do the decarboxylation. They oxidize the carboxylate. And this gives you copper 1. Then they decarboxylate it. This gives you the radical. And then they trap it with a nucleophile. In this case, the nucleophile here has a proton on this, which is lost in the end, so you get, and then they get the coupling between the R group and the nucleophile. We are still at copper 1. Sorry?
There is another hydrogen on the nitrogen.
Yeah. But, okay, let's see here. So here, like, right, you have the NH2, but that is lost probably as a proton. But that's the interesting thing, right? So how does this coupling work? It's not getting lost as a, do you think the proton could somehow become a hydrogen atom, or the hydrogen atom could become a hydride in order to oxidize? So you have the proton and the copper 1 is getting oxidized and is reducing the proton to an H atom or H minus. I haven't really seen this. Sorry? Yeah. How do you do this? So I have my radical, I have the nucleophile. So you said something about a cation. So how do you get the cation? If you want to go from here, it's a good idea. So Sangeeta has a good idea. If you want to go from the radical to the cation, what do you need to do? Is that you're losing an electron, right? So the copper 1 will become copper 0 because you need to give the electron to somewhere. You're not doing this, right? If you want to be, you see, this is the point. If you want to be catalytic and you have copper 1 here and you want to go back to copper 2, you will have to make the anion here. You would not have to go to the cation, but you need the cation because the cation now will recombine with the nucleophile and make this and the H plus, right? That would be the formal way. So you would need a, but then if you go from here to here, this is a oxidation. So you need an oxidant. But in order to go back from copper 1 to copper 2, you need the opposite. So I see nobody knows. It's probably a good thing that he knows because the catalytic cycle is not being closed. Yoon used in his paper 2.5 equivalents. That is not a stoichiometric reaction any longer, not a catalytic reaction any longer. It's a stoichiometric reaction. And so because he needs more copper 2 to oxidize this radical to the cation and then do the coupling. And Yoon points out, I think he had in a way a good point here. He says, you know, copper is inexpensive. It is acceptable to use copper-2 as a stoichiometric oxidant. And so that's how he claimed it. And you see, the thing is, we tried something like this as well, but we tried to use oxygen as a stoichiometric oxygen, but we always trapped the radical with the oxygen rather than getting catalytic the copper-2 again and then use this in the next step to oxidize the radical. And so this was Yoon's first paper, and then he subsequently showed, he did the right move. What would you do if you have read this paper? You would say, okay, copper-2 might be an inexpensive stoichiometric oxygen, but even more inexpensive would be probably iron 3, right? And so he did the same chemistry again very nicely and showed that you can also use iron 3 in this, but again, very importantly, stoichiometrically. You're not able to close the cycle. Okay, so this was one case, and interesting, Wacker process. You need to think about this. In the Wacker process, you're absolutely right. That is a palladium-2 process where the palladium becomes palladium-0. You need to reoxidize the palladium-0. You use copper-1 for this, and then ultimately use oxygen as a terminal oxidant, right? And you're absolutely right. That worked in the ionic reaction, but the problem with the oxygen here is that these radicals, if you have a radical and oxygen, they typically get very efficiently trapped. And so that's why this, in a Wacker reaction, it works because you don't have radicals, so that the oxygen can reoxidize your copper-1 to copper-2, and then in turn the copper-2 can oxidize the palladium-0 back to palladium-2. In the ionic regime that works. In the radical regime, you have the problem that oxygen is itself a radical. Again, it's a persistent radical, and it will trap transient radicals very efficiently. And so you can see how Yoon had to use that to avoid this, that he carried out that chemistry in a glove box. Okay. Want to show you again, want to discuss with you again another way, closing catalytic cycles. So here's both of the reactions you have seen, but we have not really went a lot into the mechanism. And I guess, wait a minute, I have a free page here now. Okay, very good. And you see, it's in both cases, it's one of these Giese reactions where you form a radical. Ultimately, you have this moiety, but ultimately the reaction is that you form a radical, and this radical will add to an electron withdrawing alkene, and you form the new radical, and then ultimately somehow the end product is having a hydrogen here on this. So you see, it's both times, it's the same reaction, but in the one case, it's started by a hydrogen abstraction from a chlorine radical, which we get from iron 3 chloride. And in this case, it's a Photoredox process. This is this Okada technology. We discussed this, where an electron gets injected into the phthalimide moiety, and then ultimately this is fragmenting, making the adamantal radical here, and then the adamantal radical is trapping the alkene. And you can see that there are different things which are being used. So in this Okada scenario, he's using this. We have been using essentially the iron 2 chloride, and I told you in principle the radical which we are forming, if the radical gets reduced to the carbanion, in principle, iron 2 could have reduced it, and then this way getting iron 3, and that would have closed the catalytic cycle. But in order to do this, you remember we had this anthracene as a mediator in between in this. But this would have closed the catalytic cycle. How is the catalytic cycle closed here in the top reaction? Because ultimately you need somehow also to get the same type of product, right? So here is the hydrogen which ends up in the product. And you go from ruthenium 2, this is ruthenium 2, you go to ruthenium 3, and this is the electron you inject here into the system. So now you need to bring back the ruthenium 3 back to the ruthenium 2. How do you do this? You cannot do it like this here, right? Here the iron 2 is getting oxidized. But here we have an initial oxidation, ruthenium 2 to ruthenium 3 to get us the electron. So now somehow we need to have a reduction in order to bring it back to the ruthenium 2. So how does it work here? Does anyone see what is happening here? The interesting thing is it must be to have to do something with this reagent here, which allows you to do a hydrogen transfer and then subsequently will be able to reduce the ruthenium 3 back to the ruthenium 2. Right? And so importantly to understand here, in the one case we need an oxidation to bring back our photocatalyst, because we have done this by the action of iron 3 chloride goes to iron 2 chloride. So we have an initial reduction, and so we need a final oxidation in order to go back. And here we have an initial oxidation of the ruthenium 2, and we need a final reduction to bring it back. And so in our scenario here, the proton or the hydrogen comes, the proton can protonate the anion if this is being formed through the oxidation of the iron 2. But the same thing cannot happen here in the top case. And so this is the question would be, how do you do this? Do you see how that works? Let me go back here. So we have this is the radical which we have. And then we have ruthenium 3, which we want to bring back, right, to ruthenium 2. But now you see we have these type of as a hydrogen donor. And if this acts as a hydrogen donor, then we get the product. That's good. We still have only our the ruthenium 3, but we are getting this type of radical. And this type of radical really would like to get oxidized. Because if this gets oxidized, you can see that I can draw a resonance structure which could give me the pyridine ring here. And so in this moment, if I have ruthenium 3, I need to do an oxidation, and this will allow me to go back to ruthenium-2. So that's an interesting technique that you can do overall a hydrogen transfer in both scenarios, where you need to reoxidize your metal catalyst or where you need to do a reduction of your metal catalyst. And this idea, and this is why these Hunch esters are these dihydropyridines are very complementary, because once they transfer the hydrogen, they actually want to get oxidized, so this radical is acting as a reductant, while in the other scenario, the reduced metal is able to reduce the radical and undergo the oxidation, and then it's not a hydrogen transfer, it's a proton transfer ultimately onto this anion.
So this will be stoichiometric amount.
Bitte? This one?
Yes.
It's stoichiometric, yes. You need a stoichiometric, of course, you need a stoichiometric reductant or oxidant here in this case. There's no way around this. As we had it in all the type of reactions, right? We always use in the end a stoichiometric terminal oxidant. This can be oxygen, this can be something else, but you need, of course, a terminal. You need somewhere needs the electrons also need to come from, right? If you do, because this is, of course, also stoichiometric, right? So you need, of course, in this case, you need it. You see, in our case, in the second case here, okay, here you can argue you need a stoichiometric proton. But you're right. So that is indeed, you need here the stoichiometric, ultimately stoichiometric hydrogen atom transfer reagent, which then also can work as a reductant to close the stoichiometric cycle. Okay, so again, complementarity, but always careful, always think about what is happening with your metal catalyst, how is it changing oxidation states, and how can you go back. Okay, let's, I wanted to talk a little bit about asymmetric catalysis, but I think I will leave this out because we are running behind. And the one thing I would like to discuss with you, and don't worry, this will be not complicated, but it's a very emerging technology in the moment. I don't know, did anyone run an electrochemical reaction in your lab? Did you do this? Anyone? No. So this is something in the moment which I think is emerging quite a bit. And when we talked about this, we had one question earlier, somebody wrote to you, it has become easier to do it, and it's exactly right. It's, you can buy ready-made electrochemical cells. Typically, such a setup costs about 3,000 euros. That's 300,000 rupees, right? So in this range. And then you have essentially everything is ready. You have your cell, your reactors, the electrodes, and then you can start doing the electrochemistry quite well yourself. It's quite readily without this. It's also relatively easy to build it. We use sometimes graphite electrodes, so that if you buy for pencils, if you buy graphite mines, you can use them as electrodes. It's then more expensive if you have like platinum or also electrodes, but in many cases these carbon electrodes, and then you can buy them for much money from Aldrich, or you can buy them from the pencil store for nothing. They work pretty nicely, and then you have to just put on clamps on this, and then you have your chemical cell. And the reason that becomes in the moment so popular, I believe, is also because photocatalysis became so popular. And think about this, in the Photoredox catalysis, we are shuffling electrons back and forth, right? So we're giving an electron to a substrate, we're taking an electron to a substrate. And this, in principle, can a you can also do by electrochemistry. So you can get an electron from your electrode, or you can take an electron from the electrode. So that is an interesting approach. And in addition, we talk a lot about closing electrocyclic cycles. But that closure can come because you have an electrode as a reservoir of electrons, or as a reservoir to take away electrons. So you might not have the same problems of the catalytic cycle because you have essentially excess electrons or holes available. And I think this is what makes this makes electrochemistry really quite popular in the moment. And so I have given you here just from a tutorial review. This is a really fantastic perspective here, new trends in electrocatalysis, where you can read more about electrochemistry, and they explain this a lot. But in principle, you have your electrochemical cell, and this can be a divided cell, as I've shown it here, where you have a cathode and anode in two different areas, and you just connect them by a salt bridge so that you can have the charge flow, or you can have it also in the same pot, a so-called undivided cell, and do the chemistry there. And again, it works in a related way to photocatalysis, but it's a little bit different in this way that you can, and it's the most of the reactions, and I'm probably the only reactions because otherwise you're running out of time, is I will show you which will take place on the anode. And so the anode, if you do a reaction on the anode, you do an oxidation. And so essentially what you do is you have your substrate. Let's take, because we will see this in a moment, let's take a halide, I2, and if you oxidize this, you might get 2I plus, right? So you might be able to do an oxidation on the anion, anode. And so in order to do this is you need to take away 2 electrons. And then these 2 electrons have to go somewhere. And that is why most of the reactions you see in this scenario, because then on the cathode, simply an acid might be your electron acceptor. And so on the cathode, typically, what happens is that you generate hydrogen all the time. And so this is essentially now your catalytic cycle, right? You take away 2 electrons here from your substrate, and you carry the 2 electrons to the cathode, and there you need to get rid of them any longer. But if you have an acid present, you just reduce hydrogen. You just reduce the proton and make hydrogen. And so this is a scenario which works quite nicely, and most of the applications indeed go with this, that you start with an oxidation on the anode, and in principle you could also start reactions at the reduction of on the cathode, but this is not as often seen. And so again, there's a second review also. You see this all pretty new reviews where people simply show what you can already do. And so that we just understand this, let me just show you a few examples. And so here's an example which, if you analyze this, you have a styrene here, and you have a nucleophile. You have a nucleophile here with this, and then you do this reaction in methanol. And you see what you're doing in the end. You're essentially doing an amino alkoxylation of your alkene. Right? And if you would do this, think about this in an ionic way, think about this, what you would do. If this would be the nucleophile, if this would attack here, this electron pair would go out, you would have a negative charge. If you want to bring in this now, what will you need? What would be the synton you need? If you think about this, so you have a nucleophile, the nucleophile attacks the double bond, you would have the negative charge here. If you want to get a product like this, what would you need? You would need O-methyl plus, right? You could not use, normally methanol is a nucleophile itself. So what you do here is you bring essentially two nucleophiles to the double bond. So somehow you need to take away electrons, because that otherwise it would not work. You see, as I say, you would formally need an O-methyl plus. So you would go from methoxide MEO minus to MEO plus. That's of course not really possible. But the way this is being done here is that they use as a mediator, they use iodide, right? And so here is the reagent which you can oxidize, right? And so they oxidize essentially the iodide in this case. In this case, they make iodine. So again, this is an oxidation. And this takes place on the anode. So it's an oxidation because you take away two electrons. And now the iodine can essentially react, as we know it from electrophilic brominations of double bonds, right? It can react as an I plus A I minus type system. And so what it does here is it is forming this iodonium ion. And now this is like what the I plus is doing. You all remember the reaction of a bromination of an alkene, right? There you go through the bromonium ion, and then bromide is adding, and you form the dibromo compound. With iodine, you usually never form diiodide products because the carbon-iodine bond is too weak. And so that is thermodynamically not favored. So the I plus as an electrophile will activate this, but then normally you need a different type of a nucleophile in order to, the iodide then will not attack it because you have dissolved the CC pi bond, but you have made two very weak carbon-iodine bonds, and that's not possible. But in this case here, we have a much better nucleophile available, and so we are able to do this. And so we are able to do the first ring closure here. And then in this case, you can terminate the reaction by displacing this methanol, displacing the iodide, which then will give you the product, right? And so what you have done essentially, formally, you have taken away, you have taken one iodide. I have produced it here like this. Iodine, two iodides give iodine, but you could also think about this as a redox cycle that you say I start with iodide and I generate I plus by taking away two electrons. And this is formally the same thing when we thought about hypothetically this reaction. This is the same thing like going from methoxide to something like methoxide plus, but that is of course much harder to do because the iodide to oxidize is easy, the methoxide to oxidize is very difficult. And so this is why you need the mediator in there. If you don't have the iodide in there, you could think also, why isn't it working also without the mediator? Because my electrode could oxidize the methoxide. You need much higher current in order to do this. And so the iodide has become really popular, again, essentially to act as a shuttle. And also please note that it's catalytic. They have a pretty impressive catalytic amount here with 50 mole %, but it's overall catalytic because you see here this final nucleophilic substitution, I am regenerating, I'm throwing out iodide, and this iodide then of course can get oxidized again. So it's catalytic, and this takes place on the anode. On the cathode, the cathode reaction, because somewhere we need to get rid of these 2 electrons which we have been stolen, the iodide. But then on the cathode, probably again we have a protic solvent, we have methanol, and the methanol, 2 methanols take the electron here and will form hydrogen plus probably something like 2 methoxides, right? And so that is what counterbalancing this type of chemistry. And so I think that's a pretty good and good to understand example. And there are a number of more examples what you can do. You see here it's the same idea in this type of substrate. What they do is, in this case, you oxidize a carbanion, because you see that hydrogen is next to an electron withdrawing group, and so you can very easily take this away, so you make the anion. And we have seen in the photocatalytic reactions that you can oxidize these type of anions by photochemistry to make radicals, right? And in the same way, you can also make the anion here, but then again, if you make again iodine plus from iodide, so again the same idea, iodide goes to iodine plus. If you after the deprotonation form an anion, this anion in the first step, so in the first step you would have your anion, and this anion can combine with the I plus, to give you to do this type of iodination, right? In the previous example, we would add the I plus to a double bond. Here we're adding the I plus to a carbanion. And then if under the basic conditions, if we would deprotonate here again, then we're getting the anion here, but this is not the electrochemical step any longer. The electrochemical step is the iodination in alpha position to the electron withdrawing group. But then once you have the iodide here, if you do then the deprotonation again, and then you can see what can happen, you can eliminate now in the 1,3 elimination the iodide and form cyclic systems. And you see if you here, you can form cyclopropanes, you can also form cyclobutanes. It all depends how your tether is being chosen. And again, I think this is pretty exciting, because in principle, this should be again catalytic and iodide. Because what you do here, of course, is you generate I plus, but then the I plus combines with the cation, and then you throw out in this elimination reaction. In the end, you throw out the iodide, and then you have essentially regenerated, right? You can see that it is more or less catalytic, still relatively high amounts, but it's of course sodium iodide is of course not very expensive, and you see here in some cases they even take 1 equivalent of the sodium iodide. But again, in principle, it should be a catalytic process. And very nicely, overall, look what you have accomplished. You have made these small rings, cyclopropanes, cyclobutanes, by a 2-fold CH activation in a catalytic manner. So I think that's, again, shows you the power this type of chemistry might have. And here's another pretty exciting way to do an electrochemical reaction. See, these authors here have accomplished a difluorination of an alkene. So dibromination, trivial, right? We take the alkene and bromine. Dichlorination, also relatively trivial. In principle, chlorine, or I showed you the chlorine radicals you can get from iron 3 chloride or so, and then you can do a chlorination as well. Fluorination, not so easy. I don't think that how would you do it? If you would do it analogously to a bromination, you would have to have fluorine gas, right? I think there are only 2 or 3 labs in the world who are able to handle fluorine gas. I'm not sure anybody in indoor can do this. Probably not. No one in Regensburg can do it. You need special everything in order to, because it's so corrosive, it hits everything. And it hits also glass, because the moment it makes HF, then it's also, it eats the glass, but it also reacts with steel and everything. I think everything needs to be Teflon in order to do this. So very, very difficult. So essentially, I think 3 labs or so in the world are able to handle elemental fluorine. But see how nice how that is accomplished here. So they accomplish a difluorination. So essentially, they are able to add the fluorine, formally the fluorine to to a double bond. But what they do, the same principle which we have seen before with the 2 nucleophiles. You see, this is just it's in a way a variation, but also a very clever variation, right? So here, in this example, we have also added 2 nucleophiles to the double bond, and we have taken the 2 electrons mediated by the iodine away so that 2 nucleophiles would go to the double bond. And this is something they do here as well. They add, essentially, they don't add fluorine, they add twice fluorides, and then the electrochemistry takes care of the 2 electrons which you need to get rid of, right? And the way they do this here, again, also very nicely, they're not using iodine here, they're using iodotolerine. What am I? Yeah, okay. So they're using 4-iodotolerine. And now if you oxidize this, so ultimately what we want to do is we want to take away 2 electrons, right? And then 2 electrons and let me just put it like this. I can talk about if this is the best way, but if you take away 2 electrons, you could accommodate the 2 fluorines here, right? Because this is essentially, we have 2 F minus, we take away 2 electrons, and then we could have such an iodine 3 process. It's probably stepwise, right? It's just 1 electron is taken away, 1 fluoride might add, and then a second electron is taken away. So probably you go through something like this, and then the alkene might attack this, and so you form such an, as it's shown here, you form such an iodonium ion again. And if this gets attacked by the fluorine twice, you end up here. So you see the first fluorine attacks here, and then you still have the aryl fluorinated compound like this. And if a second fluoride is displacing this, then you go back to then you have accomplished the difluorinated compound. And so again, if you think about this, there are very few alternatives, if any alternatives, to achieve this type of transformation. And I think this is really a fantastic example which shows you what you might be able to do. Let me see, we have not too much time. left. Let me see what I wanted to show you here. Okay, maybe as one example, I show this to you here still. Look at this. They have here a alpha alkoxy ether here, and then in the end, what they are able to do is they add 2 equivalents of methanol, get added here, but then ultimately what is happening is that this bond here is being cleaved to make an aldehyde here and get rid of this phenolic group here. And again, it's the same idea. So the iodine is able to make iodine plus, and with the iodine plus is possible to do it in the same way like we looked at this before, as doing an iodination on this molecule here, on this carbon. And at the same time, the methoxy group, if you have methanolate here, might add to the carbonyl group. And then what you do ultimately is you do an epoxidation, because you throw out the iodide from your alkoxy group here. And so if this gets hydrolyzed, let me see if I see this correctly. You see now here on the oxidation state of an acetal. So if this gets hydrolyzed by water, then you're cleaving off this group and you make the carbonyl group here. And this is actually an interesting reaction, because I'm not sure if you realize that this is the one structural element. It's the one structural element from lignin. And so this might be an electrochemical way to cleave lignin into smaller parts. And that is what is being shown here. I thought, wait a minute, where is the... I'm sorry, I think I'm missing one slide here where I had the mechanism on this written up a little bit more, in a little bit better way. Right, let me just point out here what we are doing. Or since we do this in methanol, I think I should have drawn this in the other way. I'm sorry. So if I let the methanol attack here on the benzylic position, and then we open up this one here, you see then I'm getting the ketal. And another ketal here. You see if this gets protonated, then I have the semi-acetal here. If this gets hydrolyzed, I'm getting the carbonyl group here, right? And the initial iodine oxidation, of course, goes through you have an attack on the H+, which attacks the I+ attacks the enol, right? That's how that initial intermediate is being formed. And so again, this would be catalytic in iodine, and it would cleave this very important intermediate in lignin to make ultimately such an aldehyde, and the other component which you are getting out of this here is phenol. Okay, so let me see. I have given you a number of more examples where you can also, we have done iodine the whole time. There are also quite a lot of other types of oxidations you can do. You can generate nitrate radicals by oxidizing nitrite. So you see, it's always the same idea. You somewhere make an anion, and this anion you do in one electron oxidation. And so people have been utilizing these NO3 radicals quite a bit. We are running out of time here. Let me see. I give you a lot of ideas here, a lot of examples. One of the ideas, probably again in the context of photocatalysis, we have talked so often that we need to readjust the oxidation state. In order to catalyze a photocatalytic cycle, we need to bring back our metal to the original oxidation state. And there also electrochemistry can play a very important role, because if you end up with the wrong oxidation state in your catalytic cycle, then electrochemistry might be able to bring it back, right? So, and that is something. Let's see if we have a few examples here. I want to show you exactly, especially this one where you reoxidize the wrong oxidation state. So we have seen a lot of reactions where we have brought copper 2 to copper 1 and then wanted to get copper 2 back. Here was an example where they have manganese 3, but then it ends up as manganese 2 because, again, you see it very similar to what we have discussed before. So you have manganese 3 azide, and I showed you that we can do azide radicals with copper, but you can also do it with manganese. And then you have manganese 2, the reduced version, and the azide radical. And now it's the question, how do I bring back the manganese 2 to the manganese 3? That's what we discussed in the photochemical regime, and we needed oxygen, if you remember this, to bring this back. Here they just need the electron anode, and they reoxidize the manganese 2 by the electrode back to the manganese 3, and again this electron which they take away from the manganese 2 here is being used here on the cathode to complete the reaction by simply reducing a proton here on the cathode. And so this is also a very good way. You see where the examples I showed you, we were struggling in the photochemistry a lot with this idea of readjusting the oxidation state of a metal ion, and that is something photochemistry can do, electrochemistry can do. And so here in this case, apparently this azide radical formation went by itself, but also one of the variants people do a lot is they do photoelectrochemistry. So in our case, and we want to try this at some point, we had the copper 2 azide complexes, and we needed light in order to go to the copper 1 and the azide radical. And there's nothing wrong with this, that you can do electrochemistry and at the same time irradiate your electrochemical cell. So you can do the combination of photo and electrochemistry. And I think that is also a very upcoming area, and we will see this, I think, in the future quite a bit more. And so people already do this also, like I just said, copper 2 to copper 1, or so you can do the reoxidation of iron 2 to iron 3. And I show you some examples. You see I have here oxidation states which are difficult to obtain under other conditions, where you make, for example, here a copper 3 intermediate, because the nice thing is, what limits the potential you can use in an electrochemical reaction? How strong can you apply an electro potential? How strong can you go? You see, with the photocatalyst, we were limited what the photocatalyst can do itself. How strong is the reduction or oxidation power of the photocatalyst in the excited state? With the electrochemistry, you can essentially put on you don't need a photocatalyst which has a given oxidation or reduction potential. You can just increase the current, right, and make it stronger and stronger. And so typically, how strong can you go? what is your limitation? So you have a substrate which you would like to oxidize, and you just say, okay, I'm cranking up the voltage until it is willing to oxidize. And your limitation is the solvent you do the reaction in there, right? If you start oxidizing the solvent, then you will preferentially oxidize the solvent and not your starting material any longer. And so that is what where you need to be what you need to be aware of. You need a solvent which is still dissolving your organic compounds, but you cannot apply a potential for oxidation of your substrate if it would oxidize already your solvent. And you see here typically quite good solvents are solvents like DMF or very often water or so, where you can go quite high with the potential before you start running into a problem here. Okay, so I think at this point I stop. This just was meant to be a short introduction into organoelectrochemistry, but I think that's something you should keep your eyes open, maybe also discuss in your groups. Should we have the possibility to apply, to have also such technology available? It's not very expensive. As I say, in the easiest way you build it yourself. It's very often more the barrier. I had the same thing. We bought one of these electrochemical kits, but because there was one student who wanted it, but then the student was suddenly not interested, and then it was sitting in our lab, and I had to go to the students every group seminar and say, okay guys, who wants to use it? Nobody wants to use it. I said, if you do a good experiment, I give you 100 rupees, right? 100 rupees was not enough, so I had to increase the price tag. And now suddenly once they know how it works, they like it, and they do it, and they try reactions. We try especially very often to do the photo reactions and reoxidize or reduce our photocatalysts to get the catalytic cycles going. And so I think it's a technique, but it's good to have as many techniques available in the lab as possible. Okay, so I think, I don't know, what is not coffee break, tea break, Debayan is going? Lunch! Lunch, you guys must be starving. Lunch, okay, but it was until 1:15, right? The original time? What was the time? No, but when was lunch break? How bad was I?
12:40 to 15. And today you don't have now class, but tomorrow.
But it says 11, yeah. So 12:45. I thought I had 1:15. So say Debayan I think is tell him to come half an hour later.
Yeah.
Oh God. You see, you guys are nice. You guys, in Regensburg, either the students would have been gone by now, or they would go and say, you're running heavily over. You guys are so nice and just sitting there, and God, I'm so sorry. I thought I have until 1:15. And so I thought, okay, I'm 10 minutes over, that is maybe acceptable, but I'm much more over.